Okay. Laws of motion. So we're all familiar with Newton's laws of motion, so I'm not going to repeat them. But what we want to know is kind of how Newton more or less got to his laws of motion, I guess. And so, in context, why was it so, earth-shattering that Newton came up with these laws? And actually, I don't think it's really fair to say Newton just came up with these laws on his own, because he was basing some of what he was doing on the work, especially of Galileo and possibly others. So, in context, we need to go way, way back to the days of the ancient Greeks and Aristotle, and we need to look at how they thought about the world. All right. So I'm going to see if I can get this to draw us a nice little universe here. So there's one part of our universe. And here's another part. And here's another part. And here's another part. Okay, and let's just arrange them in a nice logical way. Yeah, exactly what it is. Okay? It it's a good model for its day, really. It does help to explain some things. Um, Although it's been replaced, as theories often are, when new evidence becomes available, you start to have to modify and slowly change what you think is the correct explanation for stuff, right? Um, so in Aristotle's day, you know, he basically thought that what you have here is you have, pretty sure he put Earth at the center. Essentially, you have Earth at the center of the entire universe, okay? And we can write in here E. So there's Earth at the center. Floating on top of Earth in various places, you might find some water. So if you walked to the coast, or if you live on the coast, you see that you can walk out into the water, there's earth underneath it, and you just assume that even if you go way out in the middle of the ocean, there's still earth underneath it. And there's places where the earth breaks up to the surface of the ocean, and you kind of live on those parts, right? So there's your continents and your islands and so on. And Greece, of course, has islands, and it's near the coast. So this kind of fit with where they were in the world, right? So earth, water, we all inhale and exhale, and we live in an atmosphere of air. You can feel it's there if you whip your hand through it. The wind blows and so on. So it's not nothing. There's something there, and that is the air layer that surrounds the water-earth layer. And then if you look up into the sky, you might notice that there's glowing stars and other things. And this is the layer of, ooh, like that. This is the layer of um, the fire. And so this is, kind of Aristotle's worldview. So if we go to the Earth, right, and we imagine that it's stationary at the center, is that an unreasonable thing to think that the Earth is stationary at the center of the universe? Is that unreasonable to you and I? Right. So I mean, when you tell, you know, little kids or whatever, if you tell them first that the Earth is a ball shape, they might not believe you. It doesn't look like a ball from our perspective. It looks fairly flat. Please don't make the mistake, though, to think that the Greeks thought the Earth was flat. They did not, and neither did Columbus, and no person really ever thought that the Earth was flat. Okay, no sane or educated person would have thought that. In fact, the Greeks had a very accurate um, estimation for the circumference of the Earth that was very nearly correct, somewhere within 10% off of its true circumference. And we can go through later how they actually figured that out. Um, So anyway, we're interested in motion in a universe that looks like this. Okay, so one thing is that way out here, it seems like the stars, little points of light out here in the fire layer, always keep the same relative distances from one another, but over the span of a night and throughout the seasons, they rotate and change their positions. But they don't change their positions with relations to one another. Yes, student Y. This would have been, this is tied to Aristotle. Whether he actually like completely came up with it himself, I'm not sure. But he's often associated with this type of model. Later, specifically when you talk about the astronomy of this, it's also Ptolemaic, or tied with Ptolemy, who was a Greek astronomer. I believe living in Alexandria, but please don't quote me on that. So anyway, if you look up from the Earth, you see these stars keeping the same, distances from one another, so that's where you get this concept of constellations, right? The constellation Orion, or Ursa Major, Ursa Minor, and so on. All those stars in those constellations stay the same distance, but they move across the sky, right? So you might see them towards the horizon at one point in the year, and see them, higher in the sky at other points of the or time in the year. Now understand why that is, but in their day they didn't really know. And throughout a night, you see them tend to move through the sky, right? You see the sun come up and flow around, okay, and it seems to go around the Earth, and the moon also tails it and moves around too. And then you have planets, right, which don't seem to really stick on this, but they also move in strange circular patterns that can be tied to circles and so on. So this is kind of the world according to Aristotle. Now in this world, because Aristotle had the complete picture, he described the way that the Earth was, the world was set up, the physics of the universe, right? So this is the universe itself that everything exists within. He actually thought there were literal crystal spheres out here, okay, and that there was only perfectly circular motion up out here. He also thought that there was types of life and a ladder of life tied into every level. So on the Earth layer, you have human men at the absolute pinnacle of nature, followed just a rung below by human females. So ladies, sorry about that. Well, a lot of Aristotle's ideas carried forward in the Western world, and a lot of the Greek ideas carried forward in the Western world, and got adopted into other ways of thinking about the world that were maybe not scientific. So this concept that females are lesser than males, maybe you could actually tie back to this quasi-scientific thinking of Aristotle. Although I'm sure that maybe is an older idea even than that. Totally incorrect and wrong. Am I right, girls? Right. And I'm trying to fire you up. And so then in the water you also had a ladder of life, and I believe, but don't quote me on it, again, that he had the male dolphin at the top as the most advanced water creature, and then worked its way down through to things like, maybe the lowly sea slug and so on. And then you had your air creatures. I'm not sure what the pinnacle of air creatures were, but I'm guessing, say, a hawk or something like that. And then he also thought that there might be fire beings actually as well. So they might live on the moon, and I'm not really sure what they'd be like. But I mean, it sounds funny, but it's sort of logical, right? It's a logical system. And what's important about it is it's totally devoid of mysticism. There's no real mystical aspects of this. It's not, the creator did this or that, or Zeus did this or that, or whoever the Greek pantheon of gods were. I mean, they had gods associated with everything in their lives. But this is a sort of a scientific, man can understand the universe way of looking at things, which is why we still talk about it, right? It is a quasi-scientific way of thinking. Yes? Did he believe in a pantheon of gods? Great question. I'm not really sure. Did Einstein believe in a god? It's hard to say. I don't know enough about Aristotle to know what his actual personal beliefs were. I don't know really enough to know how Greek religion fit into their everyday life. I'm not really exactly sure how, whether this was seen as blasphemous or not. I'm not sure. I know later on, in Galileo's day, going away from this view became blasphemous. Okay, as soon as you said the Earth is not the center of the universe. In later years, in the 1600s, when Galileo said that, and when Copernicus said that in the 1500s, they got in big trouble. And people did get tortured and punished and burnt at the stake for being heretics and saying that, or even providing evidence that this is not the correct view of the universe became a major problem. But we're going to get there. So let's go back to motion. How does motion work in this system? Well, I'll just use Aristotle. The Greeks had two types of motion. So motion was either natural or it was violent. Okay, motion was natural or violent. Okay, natural motion requires no force. So let's do an example of natural motion. So here we are, standing on the surface of Earth. Okay, there's a nice tree, just to show where we're at. I love having all these colors at my fingertips. It's so handy. And let's say we take a nice heavy ball and we let it go. Okay, well, what's going to happen to that heavy ball? Yeah, it's going to drop. To Aristotle, that represented straight line natural motion towards the center of Earth. Okay. Now, what if I have lit a little fire here? That's what fire looks like. I'll make it look more like fire. Okay, and I examine the fire. I will see smoke rising up. Do I need to apply force to make the smoke rise up? No, I don't. Good. So what you guys are noticing is there's 4 elements here too, and we didn't mention the 4 elements, but hopefully you kind of picked up on that there's 4 elements going on here. And Aristotle also thought in his big worldview that there were 4 elements that made up all things. He did not subscribe to the atomic theory, which was a Greek theory originally, which said that at its smallest particle, matter cannot be further divided, like sand on a beach was the kind of model that they used. That was not Aristotle's view. His was that you can infinitely divide stuff up, and that all things are made of various combinations of the 4 elements. And even people have a tie into this. There's 4 humors in people. Like, I think they're blood, bile, black bile and yellow bile, and maybe like saliva or sweat or something. Anyway, whatever. I'm not sure exactly what they all are, but everything was tied into this worldview, right? So natural motion was just these objects returning to their natural place. This ball, if it falls, must be earth and water-like. Smoke must be air and fire-like. Okay? And so this was the explanation for natural motion. Any other motion was violent motion and had to be forced. So how does that work? Well, if I have a surface, let's draw a surface here. Nice flat surface. And let's make it gray. Here's our surface, and then onto the surface, let's put a box. That's a circle. Flat. A box. Perfect. And let's get rid of this circle. Go away, circle. And if we want this box to move, what do we have to do? We got to push it. So we need to apply a force. We have to force the box. If we want the box to move, we got to force it. Okay? If we stop forcing it, it stops moving. This is violent motion. So essentially, the box will move only if we force it. Only with force. Okay? how do you explain something like, here's an example, an arrow being shot, right? So let's say we have a bow and arrow. And we shoot the arrow. What we would see is that arrow traveling through space. So what Aristotle said was, you put force into it, and it will travel along until it runs out of force, and then it will transition into natural motion. Okay? So, flies till force is gone. He didn't understand concepts like energy. He didn't understand concepts like momentum. These are much, much more modern concepts. Almost 1,500 years later, until those, maybe even more, until those concepts came around. Flies till force is used up. Then, arrow transitions to natural motion. Well, does make sense in a way. Okay? However, that gives strange arrow flights. So let's see what Aristotle thought an arrow might fly like. So we've got its natural motion like that. Or sorry, it's violent motion like that. So here's the arrow being shot up. Whoops. Getting too excited to draw my arrow here. So there's the arrow being shot up. This would be its trajectory. And then it would transition to this trajectory. Okay, does an arrow fly like that? Not really. Not really. He did give it this, though, or scholars gave it this, that there was a transition. So it would actually follow this green path. Now, that look a little more like an arrow actually really flies? Kind of does, doesn't it? And especially since we're dealing with the fact that there's air resistance. So this arrow is actually, it's slowing down as it flies through the air, right? So an arrow, I mean, I think if Aristotle went and observed very carefully, he would probably find that arrows don't stick straight down in the ground. They're usually still at a bit of an arc. But I guess you could probably explain that as it hasn't had time to get onto its total, vertical streak and so on. But really, he wasn't an observationist anyway. He was not an inductive scientist. He didn't look at evidence and then come up with ideas. He more or less philosophized. He kind of sat around and thought about things and used some of his previous experiences to sort of come up with plausible explanations. And they're good. They are very plausible, right? To someone without a lot of background experience, this, yeah, okay, that makes sense, and off I go with my daily life, right? Are you good with that? Okay, so this stood from the ancient Greece, days of ancient Greece, Galileo. Oh, a couple other gems from Aristotle as well. Heavier falls faster. We've covered this already. Heavier falls faster. But not only that, 2 times as heavy falls 2 times as fast. This one, I don't know. Like, I'm sure even in Aristotle's day, there must have been issues with that. Because we can drop a penny and we can drop a quarter, and a quarter is well more than twice the weight of a penny, and they will hit the ground at nearly the same time. The quarter does not hit the ground 4 times or 10 times earlier than the penny. That's ludicrous. It's easy to test that. So why did this stand? I don't know. Great question. Well, yeah, I guess you could probably maybe do that. On the surface, that seems plausible, right? Like you say, we drop a sheet of tissue paper and a quarter. Okay, there we go. That seems to bear out this heavier falls faster. But we know now, being inductive scientists, that's got to do with the fact that there's air involved. We've actually sent people to the moon and dropped things like feathers and hammers, and we've seen them fall down at the same rate. And you can Google that. And we did. Okay, yes, that's right. There's who did that? There's a BBC thing where they evacuate a chamber and drop objects. Yeah. I don't think it was Top Gear, no. Top Gear is where they dropped the Volkswagen Bug, yeah. Okay, anyway, moving along. So what did Galileo do to change this idea? Because we have talked a little bit about Galileo. What did he do? Galileo changed all of this, right? He essentially, I think his most important contribution that Newton probably picked up on, don't get me wrong, his most important contribution to this particular area, not to motion in general, but one was all objects fall at the same rate. That's important. So you do that by experimenting, right? Galileo was an experimenter, not just a thinker, not just a sitter and a thinker. He actually experimented. But what I think is, and what probably most people would say is important and helped lead Newton where Newton went, was this concept of, and it turns out it's actually an example of conservation of energy. But Galileo noticed that if you were to run an object down a ramp, that it will essentially always come back up to the same height on the other side. That is always true. So that's where we're going with this. So now he noticed that it didn't quite make it there. And he was able to deduce the fact that there's friction involved here, right? That friction is preventing it from completely reaching the original height. And what he did was he took this system and he kept changing it, right? So he'd keep the same original height of the ball. Okay, and I'm not sure why it keeps making me repick my colors. But what he did was he said, okay, well, what if I lower the angle? Okay, well, even if you lower the angle, you're still going to find that that ball, it'll just travel farther, but it'll still get to that same height that it did before. So it travels farther until it gets to the same height. And so, oops, all of a sudden it's green. And so Galileo did multiple experiments with balls, and no matter where you put this angle, whether it's here, 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 or here, the ball will just travel to that height no matter what. So he then said, well, what would happen if I just moved this to a completely flat surface? Then what happens? What if I put a ball down a ramp and I never allow it to come back to its original height? What do you think will happen to it? Exactly. Except for friction, that object will continue to roll forever. So to Galileo, this was natural motion. Okay. Now that's not quite 100% accurate, because I believe that what he thought was that the ball would travel around the Earth forever. Okay. So this is a very early concept or idea of what we now call inertia, right? That ball will continue to roll until the force acting against it, the frictional force, stops it. Okay. Ball rolls forever, right? In a friction-free world, the ball rolls forever. Okay. Newton expanded on this idea a little bit, and he changed the concept of inertia just slightly. To him, inertia was this. Inertia was an object moving in a straight line forever, rather than in a curved line. Galileo didn't understand the concept of gravity, whereas Newton did. Newton said the reason this ball goes in a circle is because gravity is pulling it towards the center of Earth. In the absence of gravity, this ball would just literally, and any object that's in motion would continue in motion forever and ever and ever. Okay? That's inertia according to Newton. So that's Newton's first law. It's the law of inertia. And he built on the ideas of Galileo. In fact, I think Newton's one of his famous quotes is, "If I have seen further, is because I am like a dwarf standing on the shoulders of giants. Okay? So you can imagine what that might look like. Here's a giant. Okay, and he can see a distance, but not as far as this little Isaac Newton. I like to imagine little Isaac Newton here, standing up on his shoulder and seeing just a little bit further. You're welcome. Of course, you know what that metaphor is for, right? And as are we, exactly. We have the benefit of sitting here, and we have 2,000 years or 2,500 years of human experimentation condensed down into one handy lesson that we just digest and you know, take for granted, right? So it's good to remember, hey, like once in a while, let's credit where credit is due. Okay? His second law. Now we've just smoked out F equals ma, no problem, without ever really thinking about where that comes from. And that is where we want to go today. We want to talk about what is F equals ma. Okay? And we're going to talk about this in the terminology of impulse and momentum. Okay? So this is new stuff. Impulse and momentum. This comes from Newton. This is Newton's this is Newton's office. This is Newton's home turf right here, impulse and momentum. Okay? So Newton's first law is the law of inertia. Newton's second law is F equals ma, but where does it come from? It comes from this. So start this off with the concept of P equals mv. And this is the formula for momentum. Here's momentum. Here's mass. And here's velocity. So we want to look at units. We've got P equals mass is kilograms, and velocity is meters per second. Okay? So the units that momentum is going to be measured in are kilogram meters per second. They don't have a special name, it's just kilogram meters per second. So what is momentum? Well, Newton defined momentum as the quantity of motion. And two things come into play in the quantity of motion: the mass of the object and the velocity of the object. Okay? And this was Newton's starting point for thinking about motion. So if an object is sitting still on the surface, it has inertia, but it has zero momentum. It's not moving. Okay? Now try to wipe your slate clean of force, but think about what you would have to do in order to make this object move. What would you have to do? Get it from zero momentum, P equals 0, to a momentum of, I don't know, say some high value. What has to change between situation A and situation B? You've got to apply a push or a pull. Perfect. This is the concept of force. You have to apply a push or a pull. But you also have to do it for what? Some amount of time. Right. So A happens at time 1 and B happens at time 2. And so if I want to give something momentum, it just makes logical sense that I have to push it. And if I push it for 0 seconds, have I really pushed it? Have I pushed it if I push it for 0 time? No, right? I've applied a force for 0 time. I slapped you 0 times. Okay? You see what I'm saying? It's unless it happens for some period of time, it's irrelevant, right? So he said if I want to give something a momentum, or even better, if I want to change something's momentum, right? Because there's a delta P, there's a difference. Delta P equals P final minus P initial, right? So there's your P final and there's your P initial. Delta P. If I want to change the momentum, then I have to apply a force on that object, and that force has to happen for a time. P equals Ft, or delta P equals Ft. That's the important thing. A change in momentum can only happen if I apply force for some amount of time. Okay? Newton recognized this, and it makes sense. Okay, so the concept of applying a force for some amount of time has a name, and that name is impulse. Impulse is the name given to a force applied for a time to an object. So, what does that look like? I equals F T. Impulse equals force times time, and an impulse will cause a change in momentum. Are you with me? Why is momentum P? Good question. Why is this symbol P? Like, is there a reason that I know of? Like, does it stand for something? I don't know. Let's pause for a moment and find out. Okay, so upon a little bit of research, P is from the Latin pater, which also gives us the word impetus, which means to rush upon. So there. Okay, so impetus. So before we called it momentum, it was called impetus. And now you know. So just before we get to the point where we're going to derive F equals ma out of this, let's think of a quick example of where we would use impulse. So I like to think about one of my favorite movies. Oh, that's not what I want, which is Raiders of the Lost Ark. And in Raiders of the Lost Ark, a giant ball rolls after Indiana Jones, right? So, so let's think about this giant ball zipping along. So it's got a velocity. You're going to see this thing, don't you worry. And it's got a large mass. So we can imagine, right, since we know that momentum, P, equals mv, this rolling ball has a very, very, very large momentum. Now let's say Indiana Jones can't outrun it, all right, so he's going to stop this ball. There's essentially two kind of opposing ways you could stop this. So let's draw our little stick man here. Well, they say the better you can draw a circle, the closer to being a genius you are. So clearly my circle's perfect. And so here's Indy, right? Well, thanks, guys. There's his famous whip. Now he can stop this ball. Oh, we'll fix that. By the way, this is being recorded, just so you know. So there's his whip. So you can imagine, right? He's going to have to apply an impulse in order to change the momentum of this object, right? So he wants to bring the momentum from whatever high value it's at down to 0. Okay? He can do it in two ways, right? We said that you can apply a force for a time, change in momentum. So you can probably imagine that you can either change this momentum, delta P equals F times T, with a very large force over a very short amount of time. Are you with me? Or you could apply a much smaller force for a larger amount of time. Okay? Which do you think is better for the survival of Indiana Jones? Right. And we kind of laugh at this example, but in reality, you're interacting with this kind of equation all the time, right? So think about you driving in your car. Your car, and you along with it, are a large mass and you move very fast. And if you need to stop, it's much better to use your brakes, which is a comparatively small amount of force, but it takes you much longer to stop than, say, driving your car into a brick wall, right? Which is large force, low amount of time, right? That's not what you want to have happen if you like being alive, okay? So now from this, you might say, okay, so Newton has impulse and he has momentum and so on, but we don't talk about impulse and momentum in Newton's laws. Why is that? Well, it turns out that if you say, okay, Ft equals delta P, and we start to pull this formula apart, what you're going to see is you're going to see, that you get this. So a force acting for a time is going to change. Let's just see what we have here. So P final minus P initial, right? So P final, so our final velocity, so mass doesn't really change, right? So our second velocity, whatever it happens to be, in the case above it was 0, but it might just be slower, or it might be higher, it doesn't really matter, okay? Minus the initial scenario, V1, is equal to force times time. Does the mass usually change in a scenario where an object is speeding up or slowing down? Very unlikely that you're going to change mass, but velocity you can change, right? So the changeable part of momentum is oftentimes just the velocity. So what we can then do is we can distribute out mass. So we get, mass equals V2 minus V1. Now we said Newton's second law is in terms of force, right? So what if we isolate for F? Then you might get this. What do we call delta V over T? And I guess we could more likely call this delta T because it's a range of time, it's a change in time. But you get delta V over T, which is what? Good. This is also known as acceleration. From that concept, we arrive at F equals ma. Okay? Newton himself never wrote F equals ma. He talked about this in terms of impetus and changes in momentum and impulses. Okay, so that's where we get that concept from. Okay, so now we've covered impulse, we've covered momentum. So we need to do some math with it. Okay.